So we're going to learn about point discontinuities. We touched on them last class, but we didn't really go into too much depth, right? So now we're going to just kind of go a little bit further. So a point discontinuity, just to formally address this, is a hole in the graph. Let me get a thicker pen. I mean, it's kind of a simplistic definition, but it gets the point across. So I'll just do a quick sketch because, I mean, I could give you the wordy definition, but a picture's worth 1,000 words. So we did this last time where we had some kind of graph, and in the graph there was a gap. There was a point where it was undefined, and it doesn't really show up in the calculator, but it's there, when you go into the table. So I'll show you a more precise example in a minute, but it's the kind of thing where, it's very easy to miss it. So we want to follow the process, which I'm about to get to. Right. So the first thing you're going to do is factor the rational function. See if there's any common factors between the numerator and the denominator. All right. So see if there's any common factors in the numerator and the denominator. Right. We're going to extract the common factor, assuming there is one, set equal to 0, and solve. All right. This is going to give me the x value of the root of the whole. Substitute into the simplified form of the rational function. To find the y coordinate of the whole. All right. Oh, it's kind of a lot. Factor the rational function. See if there are any common factors in the numerator and denominator. Extract the common factor. So we're assuming that there actually is a common factor. Extract the common factor and set it equal to 0 and solve. That's going to give us the x value of the whole. Once you do that, we simplify the rational function and substitute that x value and find the corresponding value of y. All right, I'll show you in action, just so you can see that it's not as complicated as maybe I'm making it seem at the moment. All right. It does rely on your ability to factor, so that's always a thing. This case, the first two examples here really aren't that bad. Right. So, and you can see the directions sketch the graph of the following rational functions, but if there's a hole in it, we want to find out where that hole is. All right. We'd also have to identify any horizontal or vertical asymptotes if they exist. But it all starts with factoring. So my numerator, that's first degree, so there's nothing I could do with that, short of maybe a GCF, but there isn't a GCF there. The bottom is the difference of perfect squares. So x minus 2, x plus 2. All right. So what I'm going to do here, because we have a common factor, is I'm going to extract it from the rational function. All right. I'm going to take this whole ratio and pull it out of the rational function. So we're going to have x minus 2 over x minus 2, and we're going to set that equal to 0. All right. Now we can cross multiply here. And you could also cancel, but that would kind of defeat the purpose. So we won't do that, but what we can do is cross multiply, and you get x minus 2 is equal to 0. Okay. Basically, I'm looking for the value of x that would zero this out. And it just so happens that if it zeroes out on the bottom, it'll also zero out on the top. All right, making what we call indeterminate fraction. But for the purposes of identifying the x value, this is equals 2. Right, so that's the x value of the whole. So then once I do that, I take the simplified form, f of x is equal to, basically, oh man, my screen sharing paused. So let me pause the recording. Zoom recording. Okay. So if we simplify this fraction, the x minus 2's would cancel. You'd be left with just 1 over x plus 2. All right. So this is what I want to graph, this function here. But I also have to bear in mind that there's a hole at x equals 2. All right. So what I would do to figure out the y value of that hole is I would take the x and plug it into the simplified form. So essentially, I'm looking for f of 2, which is 1 over 2 plus 2, which is going to be 1/4. All right. So that gives me the actual coordinates of the hole, x comma y. So the coordinates of the hole would be at 2 comma 1/4. But then I'd go down this pathway here. So I'll draw a little line here to distinguish. I still need to graph that other part as if it's its own function, right? So from there, we could find the vertical asymptote. Now that we know that there's no common factors anymore, we already simplified it out, take the bottom, set it equal to 0 and solve. And you get x equals -2. So I now know that there's a vertical asymptote at x equals -2. I know there's a hole at 2 comma 1/4. Now I'm just on the lookout for a horizontal asymptote. All right. Now just going back to this simplified function, I can assume an x to the 0th power here. All right. So on the top, even if there is no visible x, it's still there. It's just raised to the 0th power. And then this x plus 2 on the bottom, that could be thought of as 1x to the 1st. So for a horizontal asymptote, what I can do is I could use those m and n rules to help me figure out what's going on. So the m value is 0. The n value is 1. We always talk about the powers. So m is equal to 0, n is equal to 1. And the relationship here is m is less than n. So by rule, that means we're looking at a horizontal asymptote of y equals 0. All right. So that's just following a rule. You could use other techniques. I mean, you could even use a graphical approach, but I think this is probably the most streamlined, where you just look at the powers. If the power is smaller on the top, the highest power anyway, is smaller on the top than it is on the bottom, the horizontal asymptote is going to be y equals 0. If it's larger on the top than it is on the bottom, then there's none. If they're the same, that's when we do that end behavior technique that we talked about last time. That I can't remember. It might come up again in this lesson. If not, I'll make it a point to review that also. Right. So I have a horizontal asymptote at y equals 0. So draw a dashed line to represent the asymptote. Y equals 0. I have a vertical asymptote at x equals -2. So it's going to be here. I have a hole at 2, 1/4. I'm going to assume that these are 1, 2. So 2, 1/4 is going to be, let's say, right around here. So I'll put an open circle there. Then I just got to figure out where the main body of the curve is going to be living. Right. For that, we could use test values, or, I mean, I mentioned this last time, you could just chuck it into the calculator. All right. So what I'm going to use test values. All right. So I'm going to test x equals 0 into f of x. So f of 0 would be 1 over 0 plus 2. So that'd be 1/2. So at the x value of 0, we have a y value of 1/2. So it's going to put me right here. So now, since I know that I'm bounded by the asymptotes, and I have to go through these two locations, the closed circle and the open circle, I am reasonably confident that this must be the path of the graph. All right, so then I would just test one more value. I'm just going to make a little bit more space here. Nothing too crazy. So I'm going to test something that's to the left of the vertical asymptote. So I'm going to test x equals -3. You test whatever you want. That seems to be the most convenient. So -3 plus 2 on the bottom. That gives me a -1. 1 over -1 is -1. So at the x value of -3, which would be about right here, we're going to go down 1 unit and plot a point. So since it has to be bounded by the two asymptotes, it's got to look something like this. And that would be my rational function. All right. There's a lot going on with a question like this. A lot of stuff to be mindful of, and which means that there's a lot of stuff to lose track of. All right. So, that could be it can be tricky, but if you follow a procedural approach, look for the presence of a hole based off of whether the function is factorable. Then if it is, find the hole, then look for your vertical horizontal asymptotes, and then test points to see where you fall in the graph. All right. Some of them are easier though. Like number 2 is really not difficult. It's just you still have to do that first step of factoring, right? And you could all like I talked about last time, you could always check your work by going into Grapher. Let's see. Get rid of this one. Type in f of x equals, create a fraction. Well, I guess I'm putting it in the bottom first, x squared minus 4. And on top, x minus 2. Hit OK. Go to the graph or go to the table. It doesn't matter. Mine is set for something I was doing in another class, so I'm just going to make it auto. So this is what my graph looks like. If you navigate, follow the point along. When you get to the x value of 2, oops, and it's very sensitive. When I get to the x value of 2, it says undefined. All right, so that's how you know there's a hole there, even though it doesn't look like there's a hole there. Right. So for the second one, again, we want to factor. So we're looking at g of x. Oops, stray mark there. On the top, if you factor it, you get x plus 2, x plus 2. On the bottom, you have an x plus 2. So we have a common factor that we can extract. All right, so this one and this one. So we're going to take that. I'm going to go down this pathway, set that ratio equal to 0. Solve by cross multiplying. You're going to get x plus 2 equals 0. Then solve. subtract 2 from both sides to get x equals -2. All right, so that's the x value of the whole. Now, if we simplify, we get g of x is equal to x plus 2. So to find the y value of the whole, all I'm going to do is replace the x in this simplified function with a -2, which is going to give me a 0, which means that I have a whole at -2, 0. All right. Now this is a beautiful problem, because you look at this and you say, okay, well, I'm going to try to find my asymptotes, horizontal, vertical, but it's not a fraction. So none of those processes apply. This is linear. You could pull the slope of 1 and the y-intercept of 2 right out of this bad boy and pretty much be done with the problem, right? Because there are no asymptotes in a linear equation. So I can plot my y-intercept of 2, closed circle. I can plot the whole at +2. I'm sorry, that should be -2. I was looking at the wrong thing. And frankly, I don't know what I was looking at. So I'd have an open circle here, and I could just draw a line because it's linear. All you need to plot a line are 2 points and a straight edge. And I have my graph. All right. A little wacky though, the way I plotted it, but that's all you would do. You know, no asymptotes, it's not curved. If you're in doubt, you go into, again, I'll take it from the top here, because I know it's kind of unfortunate with the numworks calculator. The buttons don't really light up, so it's kind of hard to see what I'm doing. So you're in the home. So I'm just going to kind of exaggerate the steps that I'm doing. Hit the right arrow to get to grapher. You go into the grapher. If you've already created a graph, that might be the thing that shows up. But I want a new expression. So I hit the up arrow. And then the left arrow to get on expressions. All right. So then I'm going to hit OK. And it brings me into this table, or this menu here. So I don't want to graph x minus 2 over x squared minus 4 anymore. So I'm going to hit the clear button. All right, hit OK to put a new function in there. I'm going to go with the original one. All right, this x squared plus 4x plus 4 over x plus 2. So I'm going to grab that second one. So down arrow, grab the one that has an f of x in it. Remember, f of x, g of x, h of x, q of x, doesn't matter. They're all representing functions, just a name. Right. So choose the one that looks like a function, hit OK, and then you can start doing your edits. All right. So, oops. So I hit the backspace. I'm going to hit the division key to create a fraction. And on the top, I'm going to hit x squared plus 4. Well, 4 is 4. X. All right. So it's this XNT key that brings up x, or at least it's the most convenient one, plus 4. And then hit the down arrow. Then x plus 2. All right. I'm trying to do a long press on the key so that you can have a fighting chance to see it. And then once you have it in and you're comfortable that you typed it in correctly, hit OK. And it'll lock it in. All right. But then you have a choice. You can go to graph. All right. So that's the middle of the top. So I'm on expressions now. It's light gray is how you know you're going into the right menu. So light gray, I see expressions. Now if I hit the right arrow, The light gray goes over graph, and if I go one further, it'll go over table. So I want it over graph. Hit OK. That's the window that the calculator chose. You can go to auto. All right, so up arrow to auto, hit OK, and it'll automatically determine a window that it thinks makes sense for the calculator, for the graph. All right, then if you hit the right arrow, left arrow, you have a moving point. So at -2, if it'll lock in on it, it says undefined, and the point actually disappeared. It fell into the hole. All right, every other point exists. This point does not. All right, so that's one way that you would know to plot a hole at -2. And if you could pull clean points off of here, then that might be all you need. Like 0, 2 is pretty clear. I mean, if you want to plot -4.8, comma -2.8, by all means, go for it. But the cleaner, the better. Hit the up arrow a bunch of times and go on to the table, and you'll get a table of values. But the one thing about this is it defaults from a 0 to 10 window. So you'd have to go to set the interval, right? Up arrow to set the interval, hit OK, and just tell it where to start and stop in terms of X. -10 to 10 is a good window. Going by ones. When it says step, it means what do you want to go by? You're going to start at -10 and you're going to go to +10. Do you want to go by twos? Do you want to go by ones? Do you want to go by half units? Whatever you want. Then confirm. Now we have a table of values going from -10 to 10. And if you scroll down the line here, you see at -2, it's undefined. All right, but every other point seems to exist. All right, so that's another way that you can get at the graph without having to do all the crazy stuff along the way. The last one here, number 3, again, same deal. We got a factor. All right, so on the bottom, I'm looking for values that'll multiply to x squared, so that's easy enough, x and x. I want to get to a product of 6. Now, looking at the top, I always encourage people to do this, and I do it myself. Like if you just make the assumption that it's going to simplify, then you already pretty much have your factors. The thing is, I don't really love the way the top is represented. All right, so this I would prefer to write as -x plus 2, switch the order. But I don't like having a negative leading coefficient. So I'm going to factor out a -1, and that's going to give me an x minus 2. All right. So this is what I would look at as my set of factors for the top. -1 times x minus 2. Now, if the x minus 2 is going to cancel, one of the factors on the bottom has to be x minus 2. So I make that assumption. And then I ask myself, okay, well, what would I have to multiply -2 by to get to a +6? It would have to be a -3. And then you could verify it, do a little distributive property, but that'll get you there. So I'm going to rewrite it just to make it look a little bit nicer. Up top, negative paren x minus 2. On the bottom, x minus 2, x minus 3. And again, because we have a common factor, I'll use the blue here. We're going to extract it. X minus 2 over x minus 2 equals 0. Cross multiply. So that 0 is thought of as 0 over 1. Cross multiply, get x minus 2 equals 0. And solve x equals 2. Then, assuming that I've extracted the x minus 2 over x minus 2, I'm left with just h of x equals -1 over x minus 3. So now, to find the y value of the whole, I'm going to find in my h of x function a 2, plug in a 2 for x, -1 over 2 minus 3. which is -1 over -1, which is a +1. So I have a hole at 2, 1. Now, unfortunately for this problem, we have all the other stuff. We got to look for a vertical asymptote. It's a fraction with a variable on the bottom, so that's how you know. All right, so I'm going to look for my vertical asymptote. We get that by setting the bottom equal to 0. So x equals 3 is my vertical asymptote. Horizontal asymptote is very similar to the previous problem, 2 problems ago. That -1 on the top could be thought of as -1x to the 0th. And the x on the bottom could be thought of as 1x to the 1st. All right, so in looking for my horizontal asymptote, I identify the m value and the n value. All right, so that's going to be the 0 and the 1. The relationship is that m is less than n. So that means my horizontal asymptote is y equals 0. And, you know, like if you find yourself getting y equals 0 as a horizontal asymptote fairly often, don't be shocked by that. It very often is the horizontal asymptote. All right. So then I could start graphing my boundaries, but I got to keep in mind, well, there's going to be curve that's in some, you know, contained by some boundaries, but not others. So if I want to go to a calculator, I can do that. But I can also just use test points. So I'm going to go out 3 units to get my vertical asymptote. Let me do this in red, actually. So that's my vertical asymptote, x equals 3. My horizontal asymptote, y equals 0. I have a hole at 2, 1. So that's going to be an open circle at this location. All right. I can look for a y-intercept. However you want to go with the test points is fine. It's just basically we need one to the left of the vertical asymptote and one to the right. All right. So I'm going to figure out, I like 0. 0 is a good number. So I'm going to, let me shrink it down a little bit. Oops. Lost part of my equal sign there. All right, so I'm going to test x equals 0, and I guess I'll do x equals 4. You know, just something to the right of the vertical asymptote. All right. So if I plug in a 0 to the simplified function, remember, even though I made it all messy like here, it really is just -1 over x minus 3. So h of 0 is going to be -1 over 0 minus 3, which is going to be a +1/3. So when x is 0, y is 1/3. So that puts a point right here, roughly. So now I can assume that I'm going through that. I got to pass by the hole and go on up to infinity. Now I just got to see what's happening east of the vertical asymptote. So I'm going to bring it in on this 4 here. So h of 4 is going to be equal to, let's move this over, -1 over 4 minus 3. -1 over +1 is -1. So at 4, so this is where 4 would be right here. I'm going to be going down 1 unit and plotting a point. So it's bounded by the vertical asymptote and the horizontal asymptote. So we're looking at something like this. And that would be my graph. And, you know, that's probably the first one and the third one are probably some of the more complicated graphs that we're going to create. You know, it's just because there's a lot going on. You know, it's not each individual skill in and of itself is not overly difficult. Is when you have to put it all together and remember to put it all together. That's when you can you run into a little bit of trouble there. Just going to move my apps around here. And again, we want to verify it. You know, we're in the grapher. Go up to expression. And just swap this out for the question that you're being asked to graph. So, I mean, I'm just going to wipe it out and do it again. So add an element, take the f of x1, make a fraction, so backspace, make a fraction on the bottom, x squared minus 5x plus 6. Hit the up arrow, 2 minus x. I mean, you could put the top in first, then the bottom. It's just when I create the fraction, it puts the cursor in the bottom, so I figured just do that. All right, then hit OK. Take a look at the picture. Make sure you're not way off base with your diagram. All right. If you're not sure, select auto. If you want to have specific windows, then you could go into axes, values of x. I'm gonna make it go from -10 to 10. Confirm. For the y values, I mean, I can leave it as is because the y values seem to be all right. So I'm making it go a little wider. So then confirm. And again, the open circle is not going to show up in the graph. Right? It's only when you start toggling along, you know, hit that left arrow. That's one thing I don't like. Sorry. Yeah, that's kind of annoying. It's actually moving the graph. I don't want it to move the graph. I want it to move along the graph. So that didn't work. But what I can do is hit the go back button. I don't know what else to call it. And then just go into the table and see where the y value is undefined. Go down the line here. We have a y value undefined at 2 and also undefined at 3. All right. But when we look at the graph, we can see there's a vertical asymptote at 3, but not at 2. So that must mean that there's a hole. All right. That's another trick that I like to tell people. Like, if you're in doubt, just look for any instance in which the graph is undefined in the table and see what that corresponds to on the graph. If there's an obvious vertical asymptote, then there you have it. If there isn't, then it must be a hole. Right. One of the, I'll say, unfortunate aspects of this course, called Precalculus, is that we covered just about every topic that one would find use of in a calculus course, which unfortunately means sometimes we bounce from topic to topic and those topics aren't as related as we might like. All right. So, because we went from polynomial functions with things like multiplicity to rational functions talking about asymptotes. And now we're going to do inverse functions, which really don't bother with either of those concepts. So it's jumping right to a new topic. I find that that's mostly the case in the first unit. In the second unit, it's more trig, focus on trig. So it kind of stabilizes a little bit, but yeah, it's very disjointed in the first unit. So that being said, go on to page 11. If you want to find an inverse of a graph, switch the x value with the y value and solve for y. All right, an inverse function is a one-to-one function right? And it is equivalent to a reflection over the line y equals x. All right. All right. Now, you'd be forgiven if you don't have instant recall on geometry concepts, but I'll show you really quickly here. If you have a point, let's say 1, 2. I'm going to just bring it in a little bit. Say you have a coordinate 1, 2. And you want to find the reflection over the line y equals x. Well, the first thing I would do is plot y equals x. Just going to get some benchmarks here. Okay, so this is my line y equals x, y-intercept of 0, slope of 1. If I want to reflect over that line, I'm basically saying find the distance from the point to the line and go that same distance on the other side of the line. Now, for drawing aside, actually, let me bring it in a little bit to make it look a little more reasonable. The reflected point would go right here. So this point here is 1, 2. This point here is 2, 1. All right. So when you reflect over the line y equals x, you reverse the coordinates. X becomes y and y becomes x. So just notation wise, r, lowercase r for reflection over the line y equals x of any point x, y becomes y, x. All right. So that's the justification for why we follow this technique. Write the equation in terms of x and y, switch the x with the y. If I'm looking for a reflection over the line y equals x, I don't have to do it point by point. I can do it variable by variable and then solve for y. All right. Little formatting issue here. I don't know what happened, but this f of x should be over here, the 5x minus 2. So it should not be over here. Let me bring the red back now. All right. So for that first example, I have y equals 4x minus 8. It's already written in terms of x and y, so I can skip that first step. Switch the x with the y. So x is equal to 4y minus 8. And then solve for y. Using ordinary algebra skills, I would add an 8 to both sides. I'd have 4y is equal to x plus 8. I want y alone, so I'm going to divide both sides by 4. It'll cancel on the right, and it'll be introduced on the left. All right, so I'm looking at y is equal to x plus 8 over 4. All right, now to distinguish this y with the y that we started with, we use a little superscript of -1. All right, so that's the inverse of y. That inverse function is x plus 8 over 4. All right, so I personally like to verify this kind of stuff. Make sure that everything makes sense. Let me not do this. So I'm going to put it into the expression menu in the grapher. Get rid of this. New element. Take the f of x. You can do the y if you want to. Let me do that just for consistency. Get that. Empty. I'm just going to type in y. So that's alpha 3. Alpha 3. Well, alpha 3 brings up a lowercase y, which is what we want, equals, so that's shift, then the pi button, then 4x minus 8. So what I can do is I can just, plot this. But I also want to get my other function in there. Now, on paper, we use the y -1 notation, but in the calculator, we're just going to type it in as another y equation. So again, alpha 3 to bring up a y, shift pi to bring up an equals, and then I'm going to use a fraction with a 4 on the bottom, x plus 8 on the top, and we hit OK. Now we have our two equations in there. Now, I mentioned earlier that it's a reflection over the line y equals x. So I'm also going to throw in a third equation, alpha 3 y shift pi equals then x, right? Now I'm going to hit on those 3 dots over here, and I'm going to change the quality of the line. Under details, it says line. Oh, you know what? I'm misremembering it. No, you can't do it that way. The best I could do at this point is change the color. All right, so that one's going to be green. All right, so the line y equals x is going to be green. The other ones will be the other ones. All right, so, oh, you know what? I didn't even have to do that. I didn't realize that you could see the color coding on the side. So red and blue, red is the original, blue is the inverse, green is the line that it's a reflection over. All right, so I can plot graph. I can do it this way. I can go up to graph at the top. Again, the window is always going to be a challenge. So auto. And, auto is auto. It's what the calculator thinks is the best viewing window. It may not be actually the case. So go into axes. I'm going to turn auto off and make this -10, +10. Confirm that. Do the same thing for y. Turn the auto off. -10, +10. And confirm twice. All right, so the green is the line y equals x. It does, it's not perfect, but it does look like the red and the blue are mirror images over that green line. So that's a good thing. You don't have to verify it every time, but it's nice to know that it does work. All right, for number 2, my first move is going to be to rewrite it as y equals 5x minus 2. Then I'm going to switch the x with the y. So x is equal to 5y minus 2. Then I'm going to solve for y, right, using ordinary algebra skills. So add 2 to both sides. X plus 2 is equal to 5y. I want to get the y alone, so I'm going to divide out the 5. Just going to write this over here. So this is the same as saying y is equal to x plus 2 over 5. But we're using function notation, f of x. Notation is the first word of the day. Notation. As in f of x notation. All right. So that y, under normal circumstances, I would replace it with an f of x and make it look something like this. But that's the same name as the original function. This is the inverse of that function, so we could use the superscript notation and just put in a -1. I don't really love the -1 notation for inverse, because when you raise a number to a power of -1, it takes the reciprocal, and sometimes the reciprocal is the inverse and vice versa. Like if I did 6 raised to the -1st power, it would give me 1/6, right? And so people have incorrectly believed, so incorrectly as it turned out, but it's totally justified in thinking this way, that all you have to do is flip whatever the function is and you have the inverse. So 5x minus 2, just make it 1/5x minus 2. But that's not what this notation means, right? The -1 notation is inverse, and under certain circumstances, it means reciprocal, right? So as confusing as that could be, it's unfortunate because I don't think it would be too crazy to just come up with a different symbol. But this is the universal symbol for inverse, right? Sometimes it's not a linear function, sometimes it's quadratic, right? But I mentioned before, and I glossed over it, I didn't really talk about it. A one-to-one function passes both the vertical and the horizontal line test. All right. A very frequent question that I get. And, I always attempt to not make the person who asked the question feel silly. A vertical line test, most of us know what that means. If not, I'll go over that in a sec. But the question was, well, what's the horizontal line test? Well, it's the same thing as the vertical line test, just with a horizontal line. So you're using a horizontal line to test as opposed to a vertical line. So I'll just draw a quick parabola here. I'll do it on the grid because it seems like that's what they want us to do. Y equals x squared minus 4. You can put that in the calculator and get points, but I'm just going to do it real quick because that's not really the point of the question. So this is the parabola y equals x squared minus 4. I always miss on the right side. I don't know why. All right, so it looks something like this. Now, the vertical line test, just as a refresher, I'm going to draw a vertical line here. All right, so for my VLT, with a vertical line test, you can draw a vertical line any point on the graph and it'll never intersect more than once. So I just kind of sweep through the graph with a vertical line and just verify that it's never going to intersect more than once. All right, and it never does, so I'm confident that this is a function. All right, so this is a function because it passes the vertical line test. VLT for vertical line test. Horizontal line test, we're doing the exact same procedure. We're just doing it with a horizontal line instead of a vertical line. So this is my horizontal line test. I'm going to sweep through the graph and see if it ever intersects more than once. And you can see beyond the vertex here, in every other circumstance, it crosses more than once. So this fails the vertical or the horizontal line test. All right, so it is not one-to-one because it fails the horizontal line test. All right, so it begs the question, can we find an inverse function? Well, we could find an inverse. It's just, it may not necessarily be a function. All right. So I'm going to follow the process that we did on the earlier problems. F of x, I'll rewrite the problem first. F of x is equal to x squared minus 4. I'm going to write that as y equals x squared minus 4. I'm going to switch the x with the y. And then we're going to solve for y. So I'm going to add 4 to both sides. That's going to give me x plus 4 is equal to y squared. Now, we reviewed this in the early part of the unit. If you have a power of 2 on one side of the equation, to get rid of that, we could take the square root of both sides. But since we're actively taking the square root, that makes this y equals plus or minus the square root of x plus 4. Right. So y is equal to the plus or minus the square root of x plus 4. All right. So what that means, kind of along the lines of a piecewise function, we have 2 parts of a graph. All right. So this means that we're looking at y is equal to negative the square root of x plus 4, or y is equal to the positive square root of x plus 4. Now, if I wanted to create the graph just based off the points, I could do that, because remember earlier I said, if you're finding an inverse, you're switching the x and the y coordinates with one another. So for example, this point over here, this one right here is -3. I'll do it in red. -3, 1, 2, 3, 4, 5, -3, 5. This one here is +3, 5. We have 2, 0, -2, 0, 1, -3, -1, -3, and the vertex is 0, -4. So we could plot all those points backwards. So I would plot -4, 0, which would put me right here. -3, -1, -3, +1. So I'm just doing a switcherooski on these. Instead of -2, 0, I'd plot 0, -2. Instead of 2, 0, I plot 0, 2. Instead of -3, 5, I'd plot 5, -3. And 5, +3. So we'd have a sideways parabola. The issue is that this would not be a function. All right. Now let me show you on the calculator what this would look like. All right, because we were able to plot the sideways parabola, but I want to actually see what these 2 equations over here amount to. So in my grapher, get rid of all this stuff. Just wiping it all out. I can put the original parabola in there, but I'm not going to. I can plot y equals, so alpha 3 to bring up the y, shift pi to bring up the equals, negative square root x plus 4. And then just do the same thing again, but with a positive radical. So alpha 3 to bring up the y. Actually, I think I almost wrote the thing that I had there. Add an element, empty, alpha 3 to bring up the y, shift pi to bring up the equals, radical x plus 4. Lock it in. And then you can look at the picture, go to graph, and you can see that it basically pieced together two separate functions and it made it into the sideways parabola, right? But what we're looking at are two separate functions. The positive one's the top half, the negative one's the bottom half. So we don't actually create one single function that represents the inverse of the parabola. We look at two distinct functions, one separate from the other. Piecing them together makes the sideways parabola. So this is actually, this part here is actually a different function from this one down here. All right, which allows us to get around the whole vertical horizontal line test rule. All right, so if it's not a one-to-one function, it's gonna have to get pieced together rather than just one continuous function. All right. Now, the last little bit here, and this is actually the last thing we're going to do for tonight, because exponential functions is so completely different from what we've been doing that I run the risk of confusing the living daylights out of people any more than I already have. So yeah, we'll just wrap it up with number 4 here. Algebraically find the inverse, and then algebraically verify your answer to part A. All right. Well, first things first. So, and again, I didn't use my notation here for the previous problem. You should have little superscripts of -1. All right. So rewrite the function as y equals instead of f of x equals. Switch the x with the y. And solve for y. Now, there's no expectation that you simplify it down nicely. As long as you get y alone, you're all right. All right. So add 2 to both sides. We're looking at -1/3 y is equal to x plus 2. You want to get y alone, you can handle it one of two ways. Divide both sides by -1/3. I don't particularly like doing that. Instead, multiply both sides by the reciprocal. So multiply both sides by a -3. I'm just going to kind of tuck it in over here. It'll cancel on the left, and on the right, it'll get allocated to the right part of the expression. Like, you're not going to accidentally divide by a -3 if you do it this way. All right, so we're looking at y equals, I can distribute here or not, doesn't matter, but I'm going to distribute -3x minus 6. And that's going to be my inverse function. Now, I glossed over again the thing about one-to-one functions. If you're dealing with a line that's neither horizontal nor vertical, it's going to be a one-to-one function. So we don't have to worry about anything crazy like what happened in the last problem. It just occurred to me that the notation originally was f of x. So I don't want y to the negative first. I want f superscript -1 of x. And it allows us to distinguish one from the other. Okay. Now, the verifying part kind of sounds strange, as if we're going to do the exact same thing again. We don't. We have a different technique. It involves composite functions. So what I'm going to do is figure out what f of the inverse of f of x is going to be equal to. All right. This notation tells me substitute the inverse of f into f of x and simplify. All right. Putting a function inside of another function. So what I'm going to do is rewrite my f of x. But everywhere I have an x, I'm going to replace it with an f negative 1 of x. So I'm going to exaggerate my substitution here. Inside, I'm putting the inverse function. All right. So I'm replacing x with the inverse function of x. And I could actually put the actual function in there because I know f negative 1 of x is equal to negative 3x minus 6. So I'm going to do negative 1/3. I'm going to replace the inverse function with what I know it really is, which is a negative 3x minus 6. And then I'm going to simplify. All right, a little distributive property. That's going to give me x plus 2 and then minus 2, which ultimately simplifies down to x. All right, so what we get out of this is a rule. F and inverse of f, they are in fact inverses if the result is equal to x. All right, so a rule if you plug a function into its inverse or plug the inverse of a function into the original function and you get an x as a result, then those two functions are confirmed to be inverses. All right. Now, if I tell you f of x is this and f negative 1 of x is that, I'm basically telling you that the second function is the inverse of the first function. So it's kind of like a little gray area, but that's the gist of it. All right. We'll next class we'll start off with this concept. I'll make up another example or two. Actually, let me make a note to myself. Make up another example. Like number 4. Just so I don't forget. So I'm going to stop the recording.